So we're looking today at shells and orbitals. Again, if you take multiple exposures, so momentary photos, you see movement captured. And what we do from this stage onwards, when we're talking about electron configurations, is we represent each orbital with a box. So here is an s orbital, and this orbital, this s orbital, can hold up to 2 electrons, and I'm going to draw them like that for now. I'll come back to why that is later. So before we go on, I've got to just make it clear that an orbital is not an orbit. It's not like a planet going around the sun in the solar system. It's not like this circular model of an atom that we looked at GCSE. And you have to be introduced on a very basic level to something called the Heisenberg uncertainty principle, which kind of says that although you can kind of know where an electron is, then you won't know where it's going next, or vice versa. Instead, you can only build up a kind of probability of where an electron might be, and it's like this picture we've seen, built up out of momentary observations that then give us a kind of map of where the electron might be. If we looked at the probability of where we are likely to find an electron around the nucleus, a 1s electron, an electron in the lowest energy level, is most likely to be kind of centred fairly close to the nucleus. It might be here as well, it might be here, it could be in all sorts of different places, but the majority of the time we kind of find an electron in this space. Now this is a 3D picture, so although we're seeing this as a flat diagram here, it's actually a spherical orbital. And the 2s orbital, so the next energy level, it could be that you find electrons fairly close to the nucleus, but actually in general they tend to be concentrated in a spherical matter, in a spherical configuration, but a bit further out from the nucleus. So we're just building up a probability map of where the electron might be. And s orbitals are spherical. P orbitals have this dumbbell shape. Because they go in 3 different directions, they can either be vertical, or they can be going in this direction, or this direction here. So there are 3 p orbitals in each p subshell. So this is the kind of diagram that we use. We've got energy that increases as we go further up. So this is our energy axis here. And at the lowest energy level we have a 1s orbital in the first energy level. It has a principal quantum number of 1 and it's an s orbital. Then we have a 2s orbital. This is a slightly higher energy here. It's got a principal quantum number of 2 and it's an s orbital. Within this same shell, we also have a 2p orbital. Now it's in the second energy level, it's in the second shell, so we give it a principal quantum number of 2, but it's p orbitals, 1, 2, 3 p orbitals, and it makes up the 2p subshell. So let's have a look at this. This here, is that a shell, a subshell, or an orbital? Pause here and make sure you understand. That is the 3p subshell. It's a subshell made up of 3 orbitals within the third shell. Oh, this is getting confusing now. This is our third shell here, all with a principal quantum number of 3. So that was a subshell. What about this one here? Pause and just make sure you know what this is. Okay, so that is an orbital. That's a p orbital that comes within this 4p subshell